Newton's first law states that an object will stay at rest or at constant speed when there is no resultant force applied. Newton's second law says that force is proportional to acceleration and also proportional to the object's mass, and mass is inversely proportional to the acceleration, combining into equation F equals ma. Newton's third law, probably the most famous one overall, states that every force produces an equal and opposite reaction force on the object. Now, these laws are all well and good, but how to apply them is the tricky bit. So we're going to look at some applications of Newton's second law first of all. So let's imagine I've got a car dragging along a trailer behind it. So a trailer that's unpowered, got camping gear in it, something like that. So as the car moves along, we're going to consider the forces acting on the car. So we've got the driving force we're going to call F. We've also got forces acting opposite. We're not going to consider air resistance or drag at this point, like we do with lots of mechanics things. But we have got force going backwards, which is the tension on the sort of tow bar coming from the trailer, because it's sort of dragging the car backwards. So to kind of put these into the format F equals ma, which is our overall expression for Newton's second law, we can say F minus T equals ma. F going forward, T going backwards, the overall car is going forwards, so therefore it's F minus T to resolve those two equals ma. Now, from the perspective of the trailer, there's no driving force, so the only force is the one that's pulling it forward. Now, this is still tension in the tow bar. From the point of view of the trailer, the tension is pointing towards the car as it's moving it along. There's no backwards forces because we're not considering air resistance, so therefore T equals ma with a small case m. Combining these two things together, we can come up with our expressions. If I've just factorised down and I add those two together, we might notice the two tension terms will cancel. So we are left with F equals capital Ma plus small case ma overall. The next situation we're going to look at, which can become a bit trickier, are situations involving gravity. So let's look at a rocket going upwards. We've got thrust pushing upwards, giving it some propulsion. We've got a weight pulling it back down, and not considering air resistance again. Now the rocket is accelerating upwards in the upwards direction. So therefore, if we put this into the format of F equals ma, we've got T minus mg equals ma, because T pointing upwards in the same direction it's accelerating. So rearranging that for T, if I wanted to find thrust, equals mg plus ma, or factorising it, we got m brackets g plus a. Next, and my favourite example is applying all this stuff to lifts or elevators. So you could do this with tension in a rope on an elevator, but far more interestingly, I like to do it with looking at the reaction force. So imagine you're standing on a set of scales on a lift, and the question is, where do you feel heavier, or where would the scales actually read slightly heavier than other times? So let's look at the forces we've got. We've got weight going down, and we've got reaction force, or the normal force, pushing back up. Now, when you have this thing called apparent weight, or when you feel heavy, that's because you have a slightly higher R, or reaction force, than you would do otherwise. So let's look at the situations first up then. We've got the elevator this time moving upwards, and it's accelerating in the upwards direction. So let's have a look at what happens to those forces. So put them into the format F equals ma. I've got R pointing up minus mg equals ma. So rearranging this for R, I can find R equals mg plus ma. Next, I'm going to have decelerating upwards. So if I'm decelerating, that's the same thing as accelerating downwards. So this time I've now got mg minus r equals ma. So rearranging that for r, I plus it to the right and take away the ma to the left. I've got r equals mg minus ma. Now I'm hoping you guys can see, regardless of what the numbers are in this equation, that r, when it's accelerating upwards, will always be higher because I'm adding together the two terms mg plus ma, whereas when it's decelerating, I'm subtracting them. So therefore you're going to have a higher apparent weight, and you can see videos of this online. You do have a higher reading on the scales when you are accelerating upwards as opposed to decelerating. Okay, next situation we're going to look at is the pulley, which if you do A-level maths, you've probably done a little bit about as well. So inside the pulley, we've got two weights, two masses. We've got capital M and little m either side of a pulley connected by one cord. Now, because it's one cord, there's a tension acting on it, and as you might be able to tell, the bigger mass is going to sort of be accelerating downwards, and the smaller mass accelerating upwards. The tension is going to be acting upwards on the left one and also upwards on the right one. So come up with expressions for these two masses. I've got m minus t equals ma, so mg minus t equals ma, and the right hand one we've got t minus mg equals ma. So just like we did previously, we can combine these two expressions together, getting rid of t, because if you add them, the t disappears, being capital Mg minus little mg equals capital Ma plus little ma. So factorising these out, I've got mg minus little mg equals a, and then brackets the two masses added together if I wanted to find out what one of those terms are. So don't memorize all these different terms, just make sure you can follow the steps of how I'm doing this. You need to be able to do this with exam questions rather than just memorizing words or key letters. So let's have a look at another way of expressing that Newton's second law, because we know it isn't F equals ma. However, we can also express it in terms of momentum. So we might remember from GCSE, F equals ma, a equals a change in velocity over time, so therefore force equals m delta v over delta t. Now, another way of saying m delta v, or change in mv, is change in momentum. So we can also say resultant force is equal to the rate of change of momentum, rate being divided by time or per second. So that's another way of expressing Newton's second law. If I rearrange this equation slightly, I can come up with this thing called impulse. So impulse is defined by force times by change in time, or alternative times by defined by change in momentum. Now we can draw, if we were to have an object hitting another object, we can draw a force time graph for that collision. And the force normally starts at 0, then increases, then decreases again for, let's say, a golf club hitting a golf ball, for example. Now from this graph, the area underneath it equals force times time, which also equals the change in momentum. So if I add some numbers here, I can work out the area under this graph, because the area of a triangle is half base times height, which in this case is going to give me 50 Newton seconds, or 50 kilogram meters per second, though both those values are the impulse. If I was also asked to find the velocity, let's say they give me the mass is 50 kilograms, I could do that as well, because I know what delta mv is 50, I just divide by 5 to find the velocity is 10. Let's take on some more collisions now. Then we've got a particle hitting a wall. It's going to exert a force. Now, as it goes in with speed u and comes back with speed u, because it's a velocity, then the speed it comes out with is negative, because it's the velocity, it's in the opposite direction. So therefore, the change of momentum is going to be mu minus mu, which gives us 2mu divided by change in time. So therefore, there's always going to be a change in momentum, so therefore always going to be a force when, for example, a particle hits a wall. So there are two types of collisions overall, and we've got elastic collisions and inelastic collisions. Elastic collisions are defined by momentum and kinetic energy being conserved, i.e. being the same before and after. Inelastic collisions, you've only got momentum being conserved, kinetic energy is not. Now, inelastic collisions are much more common in nature, so car crashes, a bat hitting a ball, that kind of thing, where energy is usually going to be transferred into heat or other forms. Elastic collisions, we can consider particles in a gas that collide to be elastic, and they're really only talking about sort of particle and subatomic levels. We consider things to be elastic. So conserving momentum, we've got momentum before equals momentum afterwards in a closed system, meaning when there's no forces being exerted on the system. And we'll look at more examples of that later on when we do the questions later on in the video. So Newton's third law, we can also use that to derive conservation of momentum. So Newton's third law says the force on object A equals the opposite direction force on object B. We indicate that with a minus sign. So if I've got change in momentum over change in time for A, change in momentum over change in time for B, but negative, then what I can do is rearrange this a little bit slightly. So change in momentum can also be expressed as mv minus mu for object A, and also for object B, mv minus mu divided by change in time. So the time taken is the same because they're both colliding with each other, so we can sort of rearrange this a little bit and say MEA, the mass of object A times by its initial velocity plus the mass of object B times by its initial velocity is equal to the same thing but with the final velocities, which is essentially what conservation of momentum is, which is really, really useful. Right, let's see if we can apply our knowledge with a few different exam questions. So you've got this one from here, from the June 2021 AS paper 2, which has got a force time graph. Now, the question asks what the speed of a ball is immediately after being hit, and the ball has a mass of 0.044 kilograms. So we should know, if you watch the video carefully, that the area under a force time graph is going to be equal to the impulse. So impulse is also equal to change in momentum, or force times time. So this the bat's impact force is increasing, then it hits a maximum, then it decreases, and then the ball is kind of left because it's got to apply force, it's got to be in contact with it. So we've got to work out the total area. So we've got a triangle over here, which has got a base of 2 milliseconds and a height of 1400 newtons. So let's work out the area there. So we got half times by 1400 times by 2 milliseconds in seconds is 0.002, which if you put that into your calculator should get you 1.4. Next triangle is slightly different. This time it takes 3 milliseconds, so we're going to have an area there of a half times by 1400 again, times by 0.003 this time, which is equal to 2.1. So therefore the total area is going to be equal to those two added together. So 1.4 and 2.1, which is going to be equal to 3.5 Newton seconds. Now, we're after the speed of the ball, so that value there in Newton seconds or in kilogram meters per second, which might make it easy to figure out what to do next, is equal to the change in momentum. So I'm just going to write that down here. So that equals the change in momentum of the ball. Now, we know what the mass is. It tells us in the question, so that leaves us a quite easy calculation to work out what the velocity is. So 3.5 equals 0.044 times by the velocity. Velocity therefore equals 3.5 divided by the mass. And that happens to be 79.54, so on and so forth, which rounds up to 80 meters per second. Just before this question, in the same paper, we've got a question about a lift, which we've just been talking through. So we've got a suitcase weighing 200 newtons when placed on a weighing scale in the lift, but the scale reads 180 newtons, so it's gone down when the lift is moving. Next, we've got options for what the lift is doing. Now, if the lift was moving at a constant velocity, those two numbers would be equal because weight equals mg. So it cannot be those two options that talk about a constant velocity. So we're left with these two, B and D. Is it either moving down with a decreasing velocity or moving up with a decreasing velocity? So let's just take each of those in turns. I'm going to draw it out just to make it a little bit easier to figure out what to do. So there's our case on the scales. Now, when we've got the weight of something on some scales, as we mentioned in the video, it's obviously got mg going downwards, and it's the apparent weight, the reaction force, that is determining sort of what the reading is on those scales. So essentially, what is happening to R in each of these. So the first instance, so B, we got moving down with a decreasing velocity. So you know lift is moving down because velocity is decreasing. That's the same thing as saying it's accelerating upwards because it's slowing down. So in that case, we know that everything's got to equal to ma. So in that case, we've got R going upwards. So it's going to be R minus mg. It's going to equal to ma. Next one, if it's moving up with a decreasing velocity, well, actually that would mean it's going to be decelerating downwards. So in that case, we're going to then have, if it's going downwards, we're going to have mg minus r equals ma. So basically, which one of these is it? Is it option D or is it option B? Well, if we rearrange each of these for r, we can then figure out which one it might be. So hopefully you guys can see that if I was to move mg onto this side here, it'd be r equals ma plus mg, which means r has actually got a bit bigger, whereas this one here, if I was to rearrange it, it's going to turn into r onto this side equals mg minus ma. Now bear in mind the scale goes down, therefore it has to be this one because it's been reduced in its reading. We don't know what how much by, we don't know the mass of it, but it has to be this one, which was our option D. Okay, the next question we've got is a bit of a tricky one. It's our sort of car and trailer scenario from earlier, but from this time it's a truck and a car. It tells us the mass of both, tells us resistive forces, so we are considering resistive forces here, and it tells us the acceleration. So out of these two scenarios, we've got both things that are accelerating in this direction with 2.3 meters per second squared. The question says, what is the tension in the tow rope? So because we've got resistive forces, basically we could actually consider the unpowered car here for the tension, because tension's going this way. From the point of view, the truck is going the other way, but it will make it a lot easier because we don't know the driving force the truck is providing. It makes it a lot easier to use the car as our situation in the first place. So generally speaking, we've got F equals ma, and the only thing that's accelerating this car is the tension force. So I'm going to change that to a T equals ma. It's not just ma here, because we know there's a bit of resistive forces going this way, then it has to be equal to the ma, the accelerating force, plus overcoming the resistive forces. So resistive forces here, it tells us in the question, are 1,100. The mass of the car is 1.3 times 10 to the 3 times by 2.3, and that's added on to 1100. Now, if you stick all those numbers in, you get an answer of basically something around about 4,100, which is option B in this question. And to finish off, we've got a situation with a rocket. So a rocket of mass 12,000 kilograms accelerates vertically upwards from the surface of the Earth at an acceleration of 1.4 meters per second. So on our rocket, we know acceleration is equal to 1.4. We know it's obviously going to have weight going downwards, and it's got thrust going upwards, and we're asked to work out what the thrust is. So setting up our equation, we've got so accelerating upwards, so T minus mg equals ma. So T we're trying to find, m we know, so 12,000 times by 9.81. Equals m, the mass again, times by the acceleration, which is 1.4. So you could have factorized that earlier if you wanted to, probably save a little bit of time to do that. So T minus, that should be there, minus mg equals this. So to find T, I've got to put this over onto this side. So that'd be basically T equals, if you wanted to do it slightly shorter, you'd have m a plus mg. But either way, you put those numbers in, you'll get 134,500, which is equal to C. Okay, let's do a couple of conservation of momentum questions to finish off. So we've got a car of mass 580 kilograms collides with a stationary van of mass 1,200 kilograms. Following the collision, the van moves off with a velocity of 6.2 and the car goes in the opposite direction with a velocity of 1.6. So let's do our before and after then. So we've got, if I can spell before, we've got a car of mass 580 collides with our stationary van. So that's going to be 0. Now afterwards, we've got the mass of the car. So we're going to say that's object A, which again goes off at a different velocity, added to now the mass, the van has a velocity, so we have to consider that as well. So the mass of the car is 580. Let's plug some numbers in. We don't know its initial velocity. So afterwards, going to be 580 is going to go backwards in the opposite direction. So we're going to say that's minus 1.6 to indicate it goes in the opposite direction. The van was 1,200 and that's going in the same direction as the car was coming initially, so 6.2. So basically after this point, it's just plugging numbers in. Okay, we've got left-hand side and the right-hand side of the equation. So if we do 580 times minus 1.6 plus 1,200 times 6.2, all we've got to do at the end is divide by 580. So to sort of get everything we need on this side, so 65112 is what that comes to, equals 580 V. So therefore V equals 6512, all that bit there, over 580, which equals around about 11.22, which is going to be option B. Let's do another situation up here. This time we've got a railway truck of mass 2,000 kilograms traveling horizontally at 1.5 meters per second, collides with a stationary truck, and then they move off together. This time we don't have to calculate everything, but we're after the speed of the trucks after the collision, and what will the effect of the collision be on the total kinetic energy. So let's work this one out first. We don't have lots of room here, so I might have to write a little bit sort of above the question. So we've got the railway truck, so 2,000 kilograms, so that's 2,000 kilograms times by the velocity, 1.5, collides with something that's not moving, so 0. Now afterwards we can add the two masses together, so we've got 2,000 kilogram truck plus the other truck is 3,000, and we know that is times by a joint velocity because they're moving off together at the same speed. So let's work out what the V is first then. There's no minuses to worry about here because everything's going in the same direction. So on the left hand side we've got this is 3,000, and the right hand side we've got that equals 5,000 V. So 3,000 over 5,000 means V is 0.6. So that narrows down our options such as these two, A and B. The effect on the total kinetic energy. Now we need to know kinetic energy is obviously equal to half mv squared. So total kinetic energy, we've got to sort of work out before and after and see if it changes or not. Okay, so let's work out at the start. So the only truck that's moving is our initial car. So the kinetic energy here of the 2,000 kilogram truck is half 2,000 times by its initial velocity squared. which equals about 2,250. And then the end, so when they're both now traveling at 0.5, the two masses added together, we can work those out. So half times by 5,000 times by 0.6 squared. So if I were to put that into my calculator, would find that hopefully those strike me as being different. Yeah, they're different kinetic energies. So therefore, it is gone. Initially, it was this much. Now it's gone this much. So it's decreased. So therefore, it's option B. So I hope you found those useful, and hopefully you got a better understanding of Newton's laws and momentum. Please leave the video a like and check out my other A-level videos.